Good.
Okay, sorry to be a little late. Thanks. So first things first. So we're going to get all the way through transformers and BERT today, which kind of represents like pretty much the state of the art in machine translation and other like types of NLP tasks. And when I was first kind of originally planning the semester, I didn't really know how this part of the semester would go. And so, anyways, I'm not really sure what to do on Thursday. I'll just put it that way. So next week we'll do just a week of like some basics in reinforcement learning. It won't feel very basic. Reinforcement learning is a little bit strange and different from the things that we've done already. But we'll just do a week of that, and then we'll have our final lecture before Thanksgiving, and then you have the week off there from the lectures, so we can work on the final project. But for Thursday, I'm not quite sure what to do. So we'll do a quick poll here with a few of us that are here, and just kind of see what people want to do. So there's a couple of options. One is we can look at, these aren't used much anymore, but they're a really interesting use of like some of the many ideas that we've been running up against, including attention, and that is neural Turing machines. So this is like, these are networks that differentiably like manipulate memory as well as their inputs and things like that. So those are quite interesting, but you don't see a whole lot of use of them after they came out. Another is to do, so that's option one. Option two is to we can do like a Q&A of what it's like to do machine learning, deep learning in industry. I did that last semester. That, for a few people that was really useful. I think for most people that was neither here nor there, but we can do that. Or third option is we can cancel it and just have the hour and a half back. So, who votes for option one? Okay.
Let's read one sentence for option one.
Oh, neural Turing machines. Option two is the industry Q&A. So there was 3, now this is 5, and then 6 actually, and option 3 is cancel. 4 for cancel. Are there any votes from those who are watching? I don't know how to actually make those questions. Does anybody know how to collect those?
It might be on chat.
Yeah, somebody like chatting there that can look. Okay, so given that very scientific poll of our class, we can do Q&A in industry. I'll just say it was a lot of fun last time. I was surprised that there were so many questions and there was so much to talk about. But you can also think of it as, those of you who voted for 3, you can basically also take option 3 that day if you like.
Might be helpful, we kind of talked about this already, but also just having like these are the defaults that you kind of should use for some of these things.
Yeah.
We talked about that a couple weeks ago.
Yeah. Yeah, maybe I can bring some of that to that.
It kind of feels like it's in together pretty well.
Yeah. Yeah. Okay. Sounds good. Okay. Decided. Is this up? I can't even tell if that's going. No, it's the wrong source. All right. Let's get going. So we have done two lectures on neural machine translation, and this will be our third and final one. So this is what we did last time. You know, this advanced neural machine translation, where we were using recurrent neural networks, and you know they actually performed state of the art when we started doing things like adding some of these tricks to them. Not tricks, but just like some of these additional techniques to them. So, you know, ways of dealing with large vocabularies, ways of dealing with very long sentences, and ways of dealing with just complexity of different languages, just generally. And even though it's super advanced, we still have lots of issues in machine translation. I went looking for like more recent ones, and I found some great ones. This one's hilarious. So Benjamin Netanyahu, Prime Minister of Israel. This is like a famous singer. I never heard of her before. Her name was Netta Biersi or something like that. I don't know how to pronounce it, but she's very famous, at least if you're in Israel. And Netanyahu is tweeting something very nice to her, complimenting her about her great performance. But it gets translated by Microsoft's translation system, and so there's a word used here that's supposed to mean something like blessing, but it's very similar to the word for cow, and it gets translated as cow. So Netta, you're a real cow. You have brought much respect for the state of Israel. So that's a horrible mistake, right? Like really bad. And again, like what makes language so difficult, right, is that there's all these nuances, especially in just, you know, less from like the book way that languages are defined or used, and more in like, you know, the way that we just use this day to day. That's a pretty bad one. I thought this was hilarious. So this was for the recent, I guess, Winter Olympics, and this is the Norwegian like chef staff for the Norwegian Olympic team, and so they ordered a bunch of eggs, and they had to do this in Chinese, and so they used Google Translate to translate the number of eggs that they wanted from, you know, this is a number actually. They wanted to translate the number of eggs that they wanted into Chinese, and so they did that, and they made their order, and it turned out that the number was 15,000 instead of 1,500. So they got 10 times as many eggs as they wanted, and there they are, kind of sitting on them laughing, I guess, not caring that the Norwegian government just picked up the bill for 9 times too many eggs. Yeah, but you know, like we trust these things that are kind of a part of our life now, but they still, you know, they are not perfect, and like not perfect in fairly simple ways. So, anyways, be really careful on your numbers, okay? You don't want to order 15,000 of something when all you want is 1,500. And of course, there's just like tons and tons and tons of these. Go searching around for it. I thought this was hilarious. This thing gets translated as high maintenance chicksel. That's exactly what it is, I guess. Yeah, you know, don't eat the carpet, it's strictly prohibited. Cream milk with coconut humans. And then I just thought this was great. So somebody's using Google Translate to write, you know, to translate their own menu. And they just admit it right up. I can't find on Google, but it's delicious. So yeah, these are a big part of our life now. It's so weird because like it's almost hard already to imagine what it was like before. Before we had these pretty readily available translation systems.
Another translation fail, which I'm not exactly sure how they were doing this, but when I was in Southeast Asia, occasionally people would interpret L's as I, and then they would like translate into Thai or something, right? Like so from Thai there. So like you might get like COIA for like cola, because they just saw a straight line and they're like, oh, that's an I, but it was actually an L because they couldn't distinguish between lowercase I and lowercase L and uppercase I. So you occasionally find like translation with that issue.
Yeah, I saw something like this. It was Fijian, and it ended up being like some sacred place had been translated as the toilets, and this was like, this became like a big deal, and kind of look stupid, I guess. Anyways, lots of ways to look stupid when it comes to language. Okay, so what do we have in store for today? So attention actually was really helped the RNN, like the seek-to-seek models, to perform better, especially with translating longer sentences. And so, creative people started thinking, okay, well, what's special about attention? Can we explore this? Can we exploit this in some way to make things better? So just as a quick reminder, this idea of attention was in the seek-to-seek models was, instead of just using like the current aggregated state for the whole encoded sentence as the input to the next hidden state in your decoder, which is meant to kind of provide context. Provide context for like how we have to translate the next word given the current input, or how we ought to produce the next word. The idea was, well, we have all of these representations from all the steps, all you think of as time steps, or all the parts of the sequence of the sentence. Why don't we just learn to like combine all those in different ways depending on what our current hidden state looks like, and then we'll use that instead as the context in which to produce this next symbol. And it turned out that's really helpful, and especially for very long sentences, because you're basically at every step you're allowing yourself to access the representation at that step way back in the previous sentence. So it may just be that you could be attending to the fact that word was back in the sentence may help in the context, and it certainly did. Remember this graphic that we had that's from this paper that introduced the idea of attention in the seek-to-seek models. That basically, these blue scores in a particular task, probably English to French, were staying high even as the sentences grew really long. And that's some major representation of like how the sentence is intending to itself during the translation. So like so for each of these words, the way it's translated, which of these was most important in, or like these are the coefficients of the linear combinations. So where this would typically be something like a kind of a straight diagonal, there's still a lot of diagonal here. Some of these things were like the European Economic Zone. Now all of these words were important in helping to translate or produce the next word in the translation to different degrees. And there's something nice here about like, hey, in French, you put the adjectives afterwards. In English, you put it before. So this has a way of being able to kind of look back and deal with that and learn how to use all that information rather than just the one aggregated context. So. So just a quick, because we're going to be doing a lot of attention here. So in the next little bit. I just want to kind of go through the basics of this again. So the idea, remember, is something like the following. You have all these hidden states. These are from the encoder. So just how this hidden state is kind of being accumulated or aggregated as you produce each of the symbols in the source segments to be translated. And then you have some sort of hidden state of the decoder, whatever step of the sequence you're trying to translate. The idea is there's some sort of similarities, way of scoring, think of it as generally as a score, but often think of it as similarity, some way of saying, how relevant is this encoding given the current encoding. So there's some way of scoring. So that you produce some numbers. You then apply softmax. This is just essentially a transformation so that this is now a probability distribution. And then you think of these now as coefficients in a linear combination. So you multiply this coefficient times the first coefficient times the first hidden state of the encoder, the second coefficient by the second hidden state of the encoder, so forth. Then you add those all together, so you have this linear combination, this actual convex combination of those sentences that's combined with the decoder hidden state, and that produces your context vector and is combined with the decoder hidden state, and then that's used to produce the next sentence. So that's it. It's really simple. It's like nice linear operations. But the important part is that it's learned, right? Like there are parameters here that are being learned, it's just part of the learning, like the training. So it learns how to attend to these encodings. Okay, so attention's all awesome. So then somebody was like, you know what? Let's just make one of these networks that all it does is attention. So there's no recurrent. So the goal here was no recurrent units at all. We just simply have like a ton of attention in this network all over the place, and let's see what it can do. So who knows how much research went into this, but the thing like one of the best ideas that kind of came out of this is something called a transformer. And being a child of the 80s, I think of Transformers as one way. Of course, Transformers movies, everybody knows what they are now, but I think of my fun little things I played with outside with the friends, but now this is what a transformer is. And it looks just as complicated. And transformer is certainly not a word that helps you understand what's going on. And this is actually quite a complicated model in a lot of ways. So we're going to take pretty much the whole time to kind of step through how this whole thing works and where all the attention is coming in here, and just how this whole thing is put together and the results that it gets. So, anyways, pretty important model. All the state-of-the-art NLP stuff is basically based on transformers now. We'll talk about one of them, which is the architecture called BERT, which is an acronym. We'll talk about that at the end, but there are a few other ones also based on transformers. So again, these are models that deal with sequential data, but without having recurrent units. So not like building up state in the way that we do the recurrent unit. Neither the encoder nor the decoder. Okay, questions so far? Before we start rolling here? I think what I have is I start off with results. So, we've seen a bunch of examples of these things. Different networks. We've reported the blue score on different translation tasks like English to German, English to French. And the important thing to see here is that these transformers, compared to all the things that we've already studied, plus a bunch of things that we haven't studied that are like other recurrent networks, we have state-of-the-art performance in a large transformer, meaning like many layers of inside these transformer encoders and decoders. So in 2017 when this was published, so state-of-the-art on these translation tasks. And again, no recurrence at all. Okay, so There's tons going on here. Inputs, they get embedded, they get some sort of positional encoding. So there's no, like I said, because there's no recurrence, there's really no, like you have to build in you have to build in certain ways of telling the sentence like where this thing is, or telling the model where this particular object is in the sentence, and there's a kind of a clever way of doing that. Positional encoding, we'll get to that. And then there's basically two main pieces to a transformer. There's an encoder, and this is showing like basically one block of an encoder, and this n times here means that you could have many of these. So like in this paper, they often had 6 layers of these things here. So instead of it just being one of these and then like the arrows going over here to the decoder, there'd be these arrows kind of going up and up and up and up 6 times. And then these things are built out of something called a multi-head attention, or something that we'll call a self-attention. A kind of residual idea that we'll talk about, this add and norm part, like a basic kind of so feed forward, so like fully connected layer idea, and again some of this residual idea, so from the res nets, and then that's it. And then you just have lots of these stacked up. That's to encode the input, and then that encoding of the input is then used in a bunch of decoding units. Again, n times. So like this block here, this large block here would be repeated however many times, 6 times in the paper. But this is a hyperparameter you can play with. It's very much like the encoder. It has very similar pieces to it. Like it has the same multi-head or self-attention part. Again, with these residual and normalization layers feed forward. But it also has an addition. Has a different attention idea too. That's part of the decoding that deals with the outputs that you're trying to either learn or produce. Okay, so there's some call-outs here. So like these multi-head attentions is basically just a whole bunch of attention stuff going on, all kind of being brought together, concatenated, and transformed. We'll go through this in detail. And then there's just there's a particular calculation for the attention that is basically like what we would expect in softmax, but has a little bit of change to it to deal with long sentences. But yeah, there you go. So lots and lots of pieces, lots of boxes, rectangles, arrows, uppercase letters. So we're going to go through this, but please stop me as things don't make sense, or if like you can't remember 10 slides before. Well, we're doing, we have to go back. If we do that too much, it'll be too long, but it'll take some time. All right. So there's all this going on, but it's kind of nice to think of this in a little bit simpler terms. So think of this whole block here just being an encoder block. That's what one of these is here. So we might have, in this case, 6 encoder blocks. Taking our input and processing it, turning it into representations that then get used in the decoder, which is again a bunch of decoder blocks, these things right here. Then again, additional processing, always being conditioned on the output of this encoder. That's what all these arrows are doing. And then finally, making predictions about the output. All right, so we're going to spend some time going through the encoder. So the encoder, like I showed, there's an attention block inside the encoder block and a feed forward block inside the encoder block, and the decoder has 2 attention pieces to it. And we're just going to focus on the encoder part for right now. So the encoder. So the first thing that happens is that you need to take your words, or your words, whatever the symbols are in your vocabulary here, so these French words, and you need to first turn them into vectors. And like we've seen, this is the same thing as like what we did with the recurrent neural networks. You can use, basically, there's so many things you could do here to encode this. You could use, basic word embedding models that embed words into vector spaces, like learn through word to vec, or other types of similar techniques. But there's some way of first starting and turning each word into a vector. So everything everything's linear algebra with some nonlinearities applied to it. So that's still the case here. And then so instead of there being like recurrent units where we first put this one in and then we put this one in and then we put this one in, and we're accumulating that hidden state as we do that, we actually we take all of these and just sort of in parallel, all pass them through this self-attention layer and produce a new representation of this vector after the self-attention, and that gets sent to this feed-forward network. So, we'll start going through the self-attention piece, right? Oh, no, we're not. I'll just say this real quick. This feed-forward piece is fairly easy to understand. There's the same set of a couple of fully connected layers with nonlinearities between them. The same network is applied to every single one of these representations after we pass through the self-attention layer to get a new representation that goes on to the next encoder block. These are again, this network's the same as this one. And when we train these things, we do backpropagation, basically backpropagating through all of the different pathways there with using shared weights. Okay, so the self-attention. How does this work? So in the encoder, it works this way. So if you remember, when we saw this in the recurrent neural networks in the seek-to-seek, the idea was we had some sort of query vector that was in the seek-to-seek, that was our current hidden state of the decoder. Then we had some key vectors to do some comparison with. Those were the states of the encoder, all the states of the encoder individually. And then we had some value vector that we used to create the linear combination, to create the context vector out of the linear combination of these things. And it turns out in the attention added to the seek-to-seek, in that model, these two were the same. But in this model, we allowed these to be different. But they're produced slightly different, well, very differently than in the RNN model. What we do is we have some learned parameter matrices here, some learned weights, and we basically we create each of these vectors. So this is just the encoder. We create each of these vectors here: the query vector, the key vector, and the value vector, simply as the matrix vector product with each of these matrices. So we learned one matrix for producing query vectors from our input. We learned one matrix for producing key vectors from our input. So like WK times that gives us that. And then we produce value vectors by learning that value matrix and doing multiplication with that input. So we're using the same information to produce each one of these things for each of the words in the sentence that we're trying to encode. So we have a representation for, in this case, thinking, a representation for, in this case, machines, and we just use the same learn matrix to produce all these things here. So this gives us like the vectors that we need to do all the attention, and it's called self-attention because, like, as you can see, we're producing all of these vectors from like a single set of inputs. Okay. So, so so in the transformer, we have many of these triplets of weight matrices that we're learning all at once, and they produce query and key and value vectors that we will. So like in this particular paper when it was first introduced, there were 8 of these sets of matrices. So you're basically you're doing attention in this way for 8 different times, and they're all learned simultaneously. So they're not, they're being, the objective function is incentivizing them not to repeat themselves, but to learn, different ways of producing these query, key, and vector functions from the same, or vectors from the same input. So that's why this is called multi-head. So it's not just like one attention mechanism or one set of attention matrices, but there can be a whole bunch of them. So in your mind, kind of think of 8 of these, because we'll see a little later when the number 8 comes back in. But it could be it's a hyperparameter like in most models. Yeah.
And try to rewrite that query key value.
Yeah, we're gonna go through this in detail now, like how this is used in this model. So anyway, what I'm going to show now is happening 8 different times. Okay, so the idea is the following. So like we already discussed, for each of the input vectors, so for each of the words in our sentence, we get some sort of initial embedding of that as a vector. Then we use these matrices. So right now we're focusing on one set of those matrices, the query, key, and value matrices, and those are producing for us a query vector, a key vector, and a value vector. Now, what do we do with all this? Okay, so with the query and key vector, we score. Basically, think of this again as a similarity between these two vectors. We score this. There's some score saying how similar these are. So this is literally just a dot product, which is related to the cosine of the angle between them, right? So the smaller the angle is, the more these vectors are like each other, and like the larger that score is going to be. It's the cosine of the angle between them multiplied by the lengths of those two vectors. So if they were unit length, both q and k, you'd have exactly the cosine of the angle between them. But anyways, dot product is your standard similarity measure, and you do this. So for one query vector, you do this for all the key vectors. So you get a similarity score for the key vector that came from this same input. And you do this for the key vector that came from the other inputs. In this case, we're just focusing on 2, but you could have 60 of these, right? One for each of the words in your very long sentence, and yeah, you'd have all these. But this is just helping us to just focus in on a few numbers. So we get this score, and then we divide it by something. So we divide it by the square root of the length of this vector here. So in the paper, the length of the vector is not 3, but 64. So the square root of that is 8. So we divide by the square root of that. That helps to. So this is like the one change from what we did before with the seek-to-seek attention. We have this additional multiplication. What this is doing is saying like. The more dimensions you have, like the more likely it can be that you get very extreme values for these dot products, and that can really destabilize the computation. So, sort of normalizing it for the length of the dimension that you're in just helps in stabilizing that a bit. It sort of tamps down on the very extreme scores you can get, and makes them sort of comparable across different runs of this same model, but with different lengths of the key vectors. So, anyways, not terribly important, but it's in the implementation. So you get your dot product, you get your score, you do this normalization, And then, this is exactly what we had before. We apply softmax so that we can get a probability distribution. And now we take these as coefficients in a linear combination. And the linear combination is not, again, with the key vectors like it was with the seek-to-seek attention, but is now with these other vectors, these value vectors. So just like some additional capacity in this network to learn value vectors different from the key vectors. And once we've done that, and we've got our two coefficients, then we do the linear combination, and that gives us like the final output from this part of the encoder block. And we do this for each of the inputs. So there would be, we go through this thing again, and this time these scores would be produced by using Q2 here. So you have a Q2.K1, a Q2.Q2, and you get these scores and apply the softmax and you get your coefficients and do linear combination, and you get your output for this word. So now what we have is some processed representation of the original inputs. But we have one representation for each of the original inputs. So that's staying the same as we go through this block.
You're just a little bit confused about what are we doing 8 times?
Oh, so there's like one set of matrices that we use to multiply with the inputs to give us these query key and value vectors, and then we'll have another set of those. Now we'll do this again with that set of vectors, or that set of matrices.
Q's.
8 Q's, 8 K's, or 8. Yeah, 8 Q matrices, 8 K matrices, 8 V matrices. So we're getting like 8 of these. So for each of the inputs, we're getting 8 of these outputs. So we have to deal with that, and we're going to get to that real soon. But yeah, that's yeah. I'm glad you asked that. Hopefully that's clarified for other people as well. But yeah, so just like as much linear algebra as you could jam into one little space, and that's what's going on here. And that's this scale dot product attention. So like this piece of it that we called out earlier, these are your matrix multiplications, the scaling. There's masking. We'll talk about masking in the decoder, applying softmax, and getting your final representation. So totally legitimate to be like, what the heck's going on? I have no idea. Like, why does this work? Whatever. That's fine. But besides that question, are there other questions? Like, yeah.
So most of them, when we say normalized, are we talking about like making the mean 0 and then dividing by?
No. So that so sometimes people use normalize for that. That's a bad way to use it. You should use standardize for doing that. You're like producing z-scores from your data. Normalize is usually when you take something and you put it on a new scale. So this is like dividing, like putting it, so like taking your vectors, you want them all to have unit length, right? Or in this case, the normalization we're doing is dividing by some scale inherent to this problem, which is in this case the length, like the dimensionality of the key vectors. But because these are dot products, like these, like Q has to have the same dimension as K, and it's typical for B to have the same dimension as well, but it doesn't necessarily have to be. But if it does, it's really nice because now, like the input that comes in here is going to be the same size as everything else in there. But it doesn't have to be. But anyways, so there's some way. So if I redo this problem now, and I instead of using length 64 vectors, I use like length 32. By dividing by the length of that, I get something that's sort of like on the same scale in both cases, right? Because I've taken into account some length scale there. It's not like dimensionality analysis. Like this isn't physics. Like there's not actually units here, but it's something like trying to put these in dimensionless units. Other questions? Yeah.
Do they share different input share same weight matrix for each Q?
Yeah. So like in this picture, we use the same matrix to produce Q1 and Q2
Okay.
by multiplying that same matrix by X1 and then by X2.
Okay.
Same thing for the Ks. We have one matrix to produce these. Same thing for the Vs.
So you have more multipliers inside. For that sentence, you have like a different Q.
Yep, exactly. So then we would do this all over again with a new triple of Q, K, and V matrices. And and in the paper we do that 8 times, but you can. That's a hyperparam. It's an architectural choice. Why 8? I don't know. It's power of 2. Always do power of 2 if you're wondering. It'll at least make it look smart, I promise. Okay. Other questions about that? Yeah.
Just trying to understand what this captures. Like, so basically each one of the queries is compared to the key of the other words, right?
Yep.
Essentially.
Yep.
So I just can't.
So this thing right here is the mechanism by which we attend to everything else in the sentence, right? So we have all these representations that, up to this point, all these things here pertain to just like that single word in the sentence. But as soon as we start doing this part, this is where we say, okay, I'm going to be more likely to attend to the value vector associated with this word if this is large, and then so forth, right? So I'm going to be more likely to attend to the value vector for the second input if this comparison is large.
Okay, so
and then,
could you say that the query vector is basically just saying, this is what I want?
Yep, that's why it's called query.
And, okay,
yep.
And key is saying,
this is what I'm like.
I'm communicating,
Yep, so this is like, this is what I want, this is what I'm like. So, and then go get the value that you're,
what you got.
So the key value thing is like a dictionary, right? It's like, what entries in this dictionary do I want? And that's what your query is about. You use the keys, to do the lookup. This is all, instead of being just like this very, binary thing that we do when we're using a dictionary. This is all has to be differential, right? We need to back propagate through everything here. So we have to have, continuous scores for how interested are we in these things? How like these things are we? We can't just have some sort of cutoff, like it's close enough or it's not. There's some continuous scoring here. And
so it does this through every single word in the sentence.
Oh yeah, and it does it through many layers. And this is only the self-attention block, so we've got a long ways to go. But this is really important here. This is like the crux of attention. Like this is the attention mechanism. This is, this word produced this query. I want to find other things like it throughout the whole sentence. I do that by computing scores. The higher this is, the more likely it is to produce a large coefficient in the softmax layer, and then consequently, I'm going to get a lot more of the value vector associated with that one than I will with the other ones. And it's all learned end to end, right? So when these things start, you just have random initialization of all these matrices, and these queries don't make sense, these keys don't make sense, these values don't make sense. But there's an objective that they're all part of, and they learn how to adjust themselves via backpropagation, right? This is the beauty of neural networks, is that there is a standard, approach to, if I have a fully differentiable system, I have a standard approach to how to adjust all those weights so that I get to, hopefully, get to something meaningful.
So it's like the softmax is basically just doing the same thing.
It's just a transformation.
That signal is doing in LSTM, right?
Yep.
That acts as a gate for how much.
We use a softmax in the seek-to-seek, or let's see. Oh, you're asking about the LSTM. No, it's not the same thing as there. Well, it depends on what part you're asking about. It's not a gate.
How much of this value is important for me to?
Yeah. Okay. So in some sense, it's like that gate. You're right. But the way that it's different is that these things aren't, like the gate values aren't independent of each other in the way, like as independent of each other as they are in the LSTM, right? Like different gates can have open flows.
Just saying how much of each.
This is just like I have all these scores, and then my softmax is a non-learned transformation, right? It's just
Okay.
it's just you know,
So it's
blind
just
line.
like how much of each word's value do I want to capture?
Yeah. Yeah.
Carry on.
Okay. Other questions? Feeling like transformer experts? I'm certainly not at all. Right, so when we do this whole thing, through each of these attention heads, we're going to get a different representation of that sentence, right? So like, here's the representation for thinking at this point. Here's the representation for machine at this point. For the first triplet of matrices, attention matrices, and then for the second, and up through the eighth. So now I have all these things. So now I don't want to pass on all these things to the next layer. I want to pass on basically like one thing. And so there's lots of ways you could have done that. The way that they choose to do this is concatenate all these together, and then learn yet one more matrix that just a linear transformation, take this from this size to this size. So again, like the sizes would be hyperparameters, but there's just one more linear transformation to take me from this concatenated set of representations just to one. So now I'm just kind of linearly combining again all the things in my representations into one representation. And again, that's going to be learned. That matrix is also going to be learned through that prop. So lots of opportunities to learn through that application. Okay, now that I got one of those things. Oh yeah, so here's all those things all put together. So I either have my initial input embeddings, or I have some representation from a previous layer. I've got my triplets of weight matrices corresponding to queries, keys, and values for each of the attention heads. Those multiplied with my input give me my query, key, and value vectors. And then through the scoring, the scaling, the softmax, I then get coefficients that I multiply with my value vectors to produce my my new representations of the input, and then I concatenate those, multiply by this matrix to get my final representation for either the original input embeddings, or if I'm deeper in the network, whatever the representation is coming from the previous layer or previous block in that. They're layers, but the previous block. Does that make sense? And then we'll just kind of keep doing this as we climb up. But of course, this is just the self-attention part. There's also the feed forward. So like now that we've done all this, these things. So you have one row here for each of the original inputs. Now these things are going to be processed by that same feed forward network to give you the final representation that would go into the next layer. Although that's not quite right, because we still have these add and norm pieces of the original network. But let's just stop for a second and kind of figure out, just kind of see what's going on here. So what you're seeing here is the same sentence twice, kind of broken out in this interesting way of parsing. This would be one way of thinking about how this network, like what the vocabulary should be. So you can see how like contractions are dealt with, at least in this way of doing it. Also like parts of speech, like the fact that this is, past participle on tire. Anyways, what you see here is you see two attention heads, and how the word it, like the attention that is being paid to that this word. So like think of this as like the query word and its representation. What other words in the sentence it paid attention to in one attention head and in another one. Okay. So the darker the color in each one, like the larger the coefficient is, like the more it's paying attention, like the higher the score was between that query and the key. So in the one, you can see what's happening is that this it is sort of referring to, or is making itself related to the word animal and the words that surround it, like the. And the it that comes, or the negation that comes in from this didn't. So for that part, for that part of the head, the representation coming out of this head is sort of combining the values from this part of the sentence, and it sort of makes sense, like just sort of grammatically. What is this it? Like if you read this sentence, we should have done that from the beginning. The animal didn't cross the street because it was too tired. So, like, what does this it refer to? Well, we know from English that it refers to animal, and this is sort of paying attention to that. You have this other attention head here that seems to be paying attention, not this time to like previous parts of the sentence that would explain what the it is referring to, but now this is like what state the it is in.
So in convolutional networks, the focus kind of learn features in each stage. Is that something similar going on here?
Yeah, you can think of the weight matrices that are in the attention head as like learning how to properly. It's hard to think of it as. I mean, these are not the matrices. This is like these are not the scores that came out of the matrices, but you can think of them as, learning to attend to appropriate parts of the sentence. Like, in some sense, they're like learning grammar. Not grammar as you would, like your English teacher would say is grammar, but it's saying like, okay, in this sentence here, this it is related to different parts of the sentence in different ways. And so, again, like one attention head, like it appears to be learning to associate it with like the actual like named entity in the sentence, whereas this one over here seems to be paying attention to something about the it, like the state that it's in. And I'm guessing, I don't have it here, but I'm guessing that if we were to look at this attention head for the word animal, that we'd see something very similar, where it paid attention to again the state that the animal is in. And there'd be other attention heads that that pay attention to different parts of the sentence. Again, trying to like extract meaning through sort of like understanding the grammar of the sentence, kind of parsing out the pieces that matter.
Attention head here means like
Triplet of them.
the 8, one of those 8.
One of those 8.
Yeah.
Yep. No recurrence so far. None. Just attention. The title of the paper was "Attention is all you need." So they're trying to prove that. Okay. So, however, there is sequential information in the sentence, obviously. If you were to rearrange the sentence kind of randomly, it wouldn't make grammatical sense. So there is information in the way, in the position of the words, and so the way that a transformer deals with that is that it attaches, basically concatenates a vector that represents the position in the sentence. So this could be like 1, 2, 3, 4, 5 kind of a thing. Like it's the first word, it's the second word. But they didn't do that. They did something way more like mysterious and exciting. But the idea is that you take these embeddings. So what I've told you so far was a little bit incomplete. It wasn't just that we were passing in the bare embedding for the input word. We're actually attaching to that something that represents the position in the sentence. And the way that they do this is through sines and cosines, where the phase of the sines and cosines is determined by the length of the vocabulary. So you get these vectors associated with like sine and cosine. So this thing, what you're seeing here is like all the possible values over a vocabulary. It's like in the hundreds here. I can't see the numbers anymore. And then here are all the time points. So like so like for the first word in the for the first word in the sentence, you basically get like all zeros coming out of the sign, all ones coming out of the cosines, and so you get a vector like that. You kind of, again, a hyperparam, you can depend. It sort of, it depends on things like the vocabulary size. But you get a vector that appends to that, or you get a vector that comes from this and you append it to there. And this is like something coming at the first position. And then we sort of move slightly forward, like 1 over the size of the vocabulary in like that fraction of the phase, both in sine and cosine. So now we get some slightly different values across the vocabulary for both sines and cosines. We get something slightly different. So like that thing in a vocabulary of size 2 is the simple representation. You have that vector representing position 2, and then position 3, and so forth. So it's like the same weird vector. And so like, again, like think of these, it's just a visualization of what these vectors are. Think of each one of these vectors here as being the vector for position 10 in the sentence, position 15 in the sentence, position 4 in the sentence. And the reason why they do this, and I have no intuition for this really, is just that like the fact that they're periodic, and you have all kinds of phases of these sines and cosines here, is like it allows it to learn some sort of repeated like positional information, like if it happens to be in there. And that this is somehow better than saying just like adding the imagery 1, 2, 3, 4, 5. You already did all your proposals already, so one like awesome project would be, what's the difference if you just use 1, 2, 3, 4, 5? Does it really change much from these crazy ways of encoding position? So again, just like really fancy ways of encoding simple things like the position in the sentence. That's a part of this. So this is one way. Well, this is like the way of encoding, like where like the sequential information. There's one more in the decoder that we'll get to in a second, but this is the part of the encoding. Questions about that? I realize I probably didn't explain that very well, but so maybe lots of questions. But maybe just believe me that there's this fancy way of looking up a vector to represent the first, second, third, fourth position. Somehow this is better than just the indicators. Okay, so moving along. So each of these like subblocks within an encoder block, if you remember the original diagram of the network, there was this add and normalize piece. And so the idea here is after doing this whole self-attention subblock that we just talked about, you then have a residual connection that connects the original embedding with the encoding from this layer. So those add together. So this is residual. Whenever we add the input to the output, we think of this as residual. So that like all this output has to learn is the difference. Whatever is the true or right representation. This just has to the network just has to learn the difference between that and the original input. So this makes it easier, like for deep models, to learn those kind of representations. And then we apply a different kind of normalization.
So is yellow X here just like green is the actual word, and X is like the embedding of the word, or what is yellow?
Yeah. So like yellow here is so like if this is the first block, this is the word embedding for this word concatenated with the positional encoding.
Gotcha.
Okay. Yeah, and then we normalize this output, and in the residual network we would have had a batch norm here, but here we have something called a layered norm, which we haven't talked about yet in this course, but it's a cool kind of normalization. So it's very much like batch norm, but instead of computing the like mean and standard deviations over all the inputs as they're pushed through to this point in the batch, you do this over the so for a single neuron, so each neuron gets normalized in your transformation layer by the way that all the data gets pushed through each of the connections to that neuron. So it's called layer norm because you're actually like normalizing each of the outputs of like a linear layer, and it has good properties. it gets you some of the same properties as batch norm, and it's robust to a lot to other things that batch norm is not. Like the statistics tend to be far more robust because your sampling number far more samples the same way because you're looking at all the inputs, like basically like all the inputs into a single neuron. You're looking at all of those, which can be hundreds instead of just like a small number in your batch, like dozens. So if you have more questions about that, we can talk about it more later. But just maybe we can just save it till a little bit later so we can get through the rest of this for the day. Anyways, just another way of doing a batch norm-like thing. And this is used in all of the subblocks, so it's used in all the encoder blocks, and it's used both after the self-attention block in the encoder and after the feed-forward subblock in the encoder. So there's residual connections around each, and you do this layer norm after the residual connection. And so there's like 2 of those within each encoder block. Okay? So that's like we've gone through all of the mechanics of the encoder block. And again, you can have any number of these encoder blocks. Here's 2, you could have 6, you could have 100, whatever. And now you know what each one of these looks like. So as we go to the next block, instead of it being the representations of this original input going into here and concatenating the positional encoding, you now have some representation that's now your input, like your full input, like this arrow here going into the next self-attention sublock and the next encoder block. Okay, so we just keep doing that same thing. We applied all this kind of parallel attention in this block, and then we just do it again to the next set of representations, and we're going to do it again to the next set. We'll do it again so everything is like really nicely encoded. Then it gets connected to the decoder. So we'll go through the decoder. Decoder is very much like the encoder. It just has this attention block that's in addition to the self-attention block. So there's one more of these sub-blocks. And we now instead of, well, I'll go through this instead of just saying I have some diagrams, but we now also in all of these blocks, like in this encoder decoder block, this is where we actually take the final representations out of the encoder, and we use those we use those as like key and value pairs in the decoder. This is how we connect up the encoding. So like you think of it as encoding the one language, and we connect it up to the decoding of the other language. Is now those encodings will be key value pairs in the encoder decoder attention block. So let's go through that right now. Maybe I should have been showing this as I was saying that. So again, go through all these encoders. We get these outputs. We now have we can produce from these key vectors and value vectors using the same mechanism that we used before, but well, let's see where right here. So so what's the difference here? So the difference in the self-attention is that between the encoder and decoder. So like they're exactly the same, except for we don't let in the decoding we don't let any, like when we're doing the attention part, we don't allow ourselves to use the value vectors from future positions. So like words that are ahead of the word in the sentence. We don't allow that. So that we basically are setting those coefficients to 0. So that's the difference between these two here. And we do that because we're imagining that, I mean, if you think about it, we're trying to do a translation task. So it wouldn't be fair if we already, like if we could use the already translated word to like help us translate another word, right? So the idea here is that we still have to be fair and, you know, produce the translation like one symbol at a time if we want to use any of the other words in the decoding. So we don't let ourselves use any words that are ahead of us in the sentence by just shutting down the ability to attend words. That corresponds to setting that softmax coefficient coming in there, setting this to 0. And then the encoder decoder, these are exactly the same things as in the self-attention layer, but it's not self-attention anymore. We still obtain query vectors from the decoding, the input coming from the output. So like from the representations of the output, but we now query those against the keys and values coming from the encoder. And this is how we connect up the two, like, you know, the two sets of languages, the two sets of sentences that we're trying to translate between. So again, query coming from the output, from like the sentence we're trying to, like the target sentence we're trying to translate to, but the keys and values coming from the source sentence that we're trying to translate. Questions about that? Okay. So is it just like totally confusing, or is that actually make some sense? No one knows the identical state theory. I was assuming totally understand everything until you ask me. So while you're formulating your questions, you guys kind of chew on this. So I already showed this at the beginning. State-of-the-art blue scores for these English to German and French translations. And it turns out these models can actually generalize well to other types of NLP tasks, but much better than some of the RNN models. So this is showing how transformers perform in like properly parsing English sentences into parts of speech. So there's this whole pen bank or pen tree bank of these parsings that is used over and over and over again for valuing models in this particular task. And this is from some subset of that database. These are sentences from the Wall Street Journal. An absolute paragon of good English, right?
So it's just trying to say like this is a verb, this is a noun.
Yep, exactly.
Why would you even do that? Like you can just look that up in a dictionary pretty easily.
Oh, you can't, right? So like there's tons of ambiguity, right? Of like if a word is playing the part of a verb or a noun. Like what is this adjective like? So what you get are these parse trees. So it's not just that like this is a noun, this is a verb. It's like, you know, this is like a prepositional phrase, and here's the preposition, and it's, you know, like here's the adjective. So these are actually really complicated and difficult.
Okay.
Yeah. Yeah. I'm guessing most of us would fail pretty badly on these. But these computers can get pretty good at it. Okay. So we have just 5 minutes left, so I have just a couple slides here to just briefly cover this. So transformers came on the scene. Everybody was super excited, state-of-the-art results. Not only in translation, but in other NLP tasks. So it's like, whoa, attention, maybe it is all you need for these things. And so then, you know, a whole cottage industry kind of grew up around transformers. And, you know, about a year later, there was this paper published that introduced this architecture known as BERT, so that stands for Bidirectional Encoder Representations from Transformers. And the idea here, so there are a couple other architectures that took advantage of transformers. One is OpenAI had these GPT, which is, let's see, it stands for like generalized pre-training transformers, something like that. Can't remember. There's now a version 2 of this where they just recently released like the billion weights from it. I don't know if you saw that, but like at first they weren't going to release all of the weights because it was like too dangerous to do. Like this model was so good that it was like dangerous in some way. And then like the OpenAI community decided that the world had respectfully used the weights from the smaller models, and then it released all the big models. So they're making moral judgments about how we use their models, I guess. But the point is that like the GPT was a way of using transformers to do more than translation, but to do like sentence level tasks. But it was still kind of like a left to right architecture. This Elmo was another one, but it was like it had left to right parts of its architecture and then right to left. So it was like in some sense bidirectional, but it was this really cumbersome model to be able to do these sentence levels. So like the task is no longer like translate in one direction, but just sort of like classify the sentence in some way, produce the next sentence, or like decide whether a sentence was the next sentence, like replace missing words within the sentence, all these sort of sentence level tasks. And Bert came along and was like, you know what, like we're just going to do transformers, and we're just going to allow there to be like it's bidirectional, but really it's like non-directional. It's like we're just going to allow all the connections, and we're not going to impose necessarily any sort of directional structure. We're just going to allow this to happen in the encoder, and then we're going to like attach classification heads to the encoder to allow us to do these things. And that's what they did. BERT really is more than anything else just like a set of like pre-training tasks, so that you can like learn these rate representations of these sentences for doing any other tasks. And they came up with these two tasks: the mass language model and the next sentence prediction. Mass language model is essentially something like we're going to replace. They say about 15% in the paper of the input with just this token mask. So we know it's been masked. And our task is simply to take the whole sentence and predict what word in the vocabulary should have been there. So think of this as kind of like an autoencoder type of thing, right? Where it's like, it's not truly autoencoding. We're still doing like some supervised task here, but the idea is like things that are masked, we want to predict it. So we're able to use like the same sentence many times to sort of pre-train. And then the next sentence prediction was very similar to it. You basically have your inputs, two sentences. You have some tokens to say like, what's the first sentence, what's the second sentence. And the basic thing here is you just make a prediction to say like, is this actually a sentence that follows this sentence here? Like, does it make sense for it to be the next sentence? So again, you can take a corpus of these sentences, and you have a whole bunch of them, and you have lots of positive pairs where they actually follow each other, and you have lots of negative pairs. Any sentences that didn't follow each other, you can put them together, and you can do this classification task. And while it seems super simple, it was a huge innovation to kind of like, come up with these pre-training tasks to pre-train these transformers. And I didn't quite mention it, but like there was this classification layer that was added on to the end of your transformer encoder to allow you to do this. So this doesn't necessarily depend on the decoder, but it gives you these great pre-trained weights for the encoder. And then you can now use these pre-trained models to do like extremely well on all kinds of sentence level tasks. So classifying sentence pairs, single sentence classifications, question answering tasks, those are really cool. Single sentence tagging, so that's like parse speed tagging that we talked about before. And it gets state-of-the-art results in this. So There's another metric for like for just basic language understanding called GLUE, General Language Understanding Evaluation. It's like 9 tasks that you have to that you get scored on, and then you get some sort of like average score to say how to compare your model against other models. And when this paper came out, it was getting state-of-the-art scores on all these language understanding tasks compared to GPT and Elmo and these other ones that were state-of-the-art at the time. Yeah, that's what BERT is. So like now there's all kinds of let's see, good. There's all kinds of like what's the right way to say this? Iterations on the BERT architecture and like how to do it. And they all have, a lot of them get clever names like Roberta or Ernie or I don't know, other clever names, but they're all kind of based on the same idea that if we use these transformers in this sort of non-directional but maybe bidirectional way, that pre-training in this way gets us to a point for our transformers to be able to do like state-of-the-art on all kinds of language tasks. And these are the things that are now showing up in like Google Translate and things of that nature. They're definitely state-of-the-art. So yeah, so that's it for today. And next time, question and answer, we'll also talk about like best practices kind of stuff. And if you have more questions on this, come up and ask me. We'll have to talk about it. Oh, I didn't mention at the beginning. I'm going through your proposals now, and I will hope to have a response to you by the end of the week. All right. Have a good one. Yeah. Yeah, right there. Make sure when you apply that know that right in there that this class. Yeah, just say that I'm teaching this class. Yeah, that's that'll be good. Yeah.
I've been there. I've been there. I think very
we'll start making decisions by niches. Yeah. Yeah, like the best interns are always wanting these things to be done.
The common thing that's
So we're already doing that.
how you figure out
Cool.
right?
Yeah, from the homework, you mean?
Yeah. I'm missing something on my derivatives.